Thank you. My work is about network security and privacy. And I'm interested to sort of problems that has a broad social impact. Roughly speaking, my research is about all these three. I invent techniques and frameworks to be able to detect network interference. I use these frameworks to be able to understand the behavior of those intermediaries which does the interference, and then use this understanding to be able to find defense and establish tools. In this talk, I want to talk about Censored Planet, a system that uses surprising properties of network protocols to be able to measure internet censorship globally. And before I dive in, I want to give you some background. If you remember in basic networking class, we learned that we have two endpoints. And the job of intermediaries in between is to route packets from point A to point B. But really today, internet is far more different from the ideal view. We have intermediaries that are intelligent. We have firewalls, network intrusion detection systems, and antiviruses. Unfortunately, the same technologies that is there to protect us can be used to harm us. It depends on who is running these systems. If they decide to be adversarial towards users, then we're dealing with a problem that I call network interference. Network interference is any action by these intermediaries that violate the basic security principles, such as confidentiality, integrity, and availability. One common example of network interference is censorship. That means several things. For example, it can mean blocking. And in extreme case, internet shutdowns, where the government just unplug internet for their citizens. Or it can mean throttling, where the ISPs decrease the internet speed so to discourage their users from accessing information. It can also mean takedowns, where a censor demands a provider to remove information. Social media, Twitter, Facebook, and Google deal with this sort of takedown requests from governments all the time. Network interference is just not censorship only. It can be targeted or mass surveillance. It also can mean tampering, where the information is being modified from source to destination. And even more, it can be used to launch attacks. Great Cannon is an example of a study we did that I briefly will talk about it. What I'm trying to say is there are many behaviors and many actors in internet communication with different conflicting agendas. So the field that I'm working in is a rich area for research that has a potentially valuable impact on ordinary people. To study network interference, we draw tools from different fields, CS and beyond. We need to know about networking, measurement, system, security, and often touches of political and social science. Over the past recent years, we have seen an alarming level of complex active interferences by nation states such as China that not only threaten internet freedom, but also internet security. And I am hoping through my research and our community's research, we can be more efficient in designing defense against these active attacks and also be able to have a sustainable safeguards for users. I want to start by shedding light in one of the studies we did around 2015, a complex network interference attack by Chinese government. In March 2015, GitHub, which is a code repository found themselves under a distributed denial of service attacks. They were receiving requests more than they could possibly answer. And after investigation by us and so many others, the reason was because somebody was injecting JavaScript into traffic coming from Baidu, a search engine famous in China. Why the attackers were targeting GitHub? It turns out because GitHub was hosting a website called greatfire.org. Greatfire.org is a website containing information about Chinese national firewall censorship and how to circumvent it. A group of us from different backgrounds, from CS, political science, and activists get together to understand this attack and who is behind it, to find evidence for such attack. So before I can talk more, I want to explain how this attack worked. If you send a request from somewhere in the world to a server in China, let's say blah.com, the Great Canon, the tools that was launching the attack, would look at your traffic, the DPI, the packet inspection, would look at the traffic and let it go. But if this traffic was for Baidu, with a probability of 1/50, your packet would be dropped, and the JavaScript was injected into response back to you. And then this JavaScript would launch requests to GitHub. In an aggregated way, then GitHub would receive millions of requests at a time, and therefore they were down for 3 hours till they figure how to deal with it. These attacks was running for almost 3 weeks and more. So we were lucky enough to be able to study this Great Canon tool while it was running. And actually, because of our experience on studying Great Firewall of China for many years, we had enough of information about how Chinese national firewalls look like, implemented or deployed, where in the network they are. And at the end, we provided enough evidence that could suggest Great Canon is very likely operated by Chinese national government, and it is co-located where the Great Firewall's other infrastructure is, but it's meant for a different reason. It's a separate system, and it shows an escalation of state-level capabilities that Chinese government had. To make this problem more clear, let me give you an example of how Great Canon can be used for endangering national security here. For example, a US defense contractor can communicate to a website that is hosted in China, and a Great Canon is watching the traffic and flows. And when they detected this traffic, they can actually inject a zero-day attack. This was just an example of a complex system we studied. But we know that censorship or interferences is a pervasive practices, and it happens everywhere, from country to country and time to time. So it makes sense that many researchers in my field and many other fields actually are interested to collect and understand internet censorship globally and continuously. There are many reasons why this is important, but let me just give you some. We want to bring transparency and accountability to where governments practice internet censorship. This transparency then can help us to come up with defense technology, where to deploy these different technologies that we came up with. And also it helps the users in different places to know what they're missing out, and to help policymakers and diplomats to have a right level of information to respond accurately and appropriately to such events. I want to state measuring internet censorship globally and continuously a little bit more formally. And the way to state it is like, we want to know whether two hosts can talk to each other, can communicate. And we want to know that for as many users around the world, to as many sites. Well, solving this problem turns out to be a very hard problem. And the best people came up with is to put instrumentation on users or site, like by installing a measurement software that the user runs and therefore collect the data that way. Or giving away a Raspberry Pi that is equipped to run censorship measurement from it. And as you can see, if you want to measure internet censorship globally, these approaches, these direct approaches, have a lot of disadvantage. First one is how many users can you find around the world to run a software for you? So it's not scalable. Also, when it comes to measuring internet censorship, you often deal with sensitive data. And it might not be a good idea to ask end users to run sensitive measurements. So ethics is an issue. And continuously, the continuity of the data is another. When a user shut down their internet or stop running the measurement, you lose a data point. So the data collected from these direct ways are usually not continuous. Several years ago, I looked at this map. There are 140 million public IP addresses that follow some protocols. We can find them, they're live. So I started asking this question: how can I leverage standard protocols that we have to be able to detect whether two hosts can talk to each other? I don't want to hack them. I don't want to find a vulnerability and exploit that. No, I just want to be able to find ways to leverage standards to detect that. And I want to be able to detect that remotely from United States. How can I do that? When I pitched the idea of that, hey, is there a way to remotely off the pass without having a root access in machines to see whether the two hosts can talk to each other or not, many people in the field said that that's impossible. It's a dissertation that is going to fail. But of course, we pursued the idea and we came up with a technique called a spooky scan. A spooky scan can help you to measure whether the two remote hosts can establish a TCPIP handshake, and if not, in which direction the packets are being dropped. Remember, we can do that without having access on them off the path remotely. It's a magic, guys. And over the past couple of years, we built a follow-up system called Augur that use a spooky scan side channels to be able to scalably and ethically measure TCP/IP blocking for us. So I want to talk about that in more details and explain how we do find that. And for that, I need to give a little bit of TCP/IP background. Internet works based on TCP/IP, or it's one of the basic old protocols exist. And for any communication that is based on TCP/IP, there is a handshake. You say SYN, the other person sends a SYNACK back, and then you ACK. It's like hi, hi back, and acknowledge, and acknowledge. And in each of these packets that goes back and forth, there is a variable called IP ID. Remember that. That's what I'm using later. There's a part of this protocol says that if you send a SYNACK packet to a machine that didn't send you previously a SYN, it's going to send the reset back. It's going to say, hey, I didn't send you hi while you're talking to me. And there is another part of the protocol say that if you send a SYN packet to a person with open port and don't do anything after, because TCP is reliable, it's going to send the SYNACK back and retransmit it. For a spooky scan to work, I'm going to use these parts of the protocol. But there are other basic requirements that I have to also meet. One of them is that IP ID variable in the packet, I need them to be globally assigned. It means that there should be a shared variable. Like Windows operating system, Windows XP or FreeBSDs, all the machines with this kind of operating system does that already. And I need the sites that I'm interested to measure have open ports or respond to me. And I need the measurement machine place I am going to run the measurement from to be able to let me spoof packet. It means sending packets with source IP being some other people's IP, not my own. So this is how Spooky Scan works. I start the scan by sending a CNAC packet to my user or reflector. It didn't have a previous scene from, it's a out of blue CNAC. So following the protocol, it's going to send me a reset back. And in that reset packet, it's going to release to me what's the current value of that IP ID variable. So I learned that, OK, right now it's 7,000. The next act I do is I send a spoof scene packet with the other machine, the reflector machine's IP, to our site. Site has open ports, see that, and said, OK, CNAC. CNAC to a person who owns the IP. So the CNAC will go to the reflector. Reflector receives a CNAC out of the blue. Following the protocol, it's going to send a reset. And while doing that, the IP ID is going to be increment by 1. Then the next act I do is I do again IP ID query. I send a CNAC again to the reflector, and I looked at the value of the IP ID in the response. So in my view, there is going to be 7,000 and 7,002. So there is a jump in between. So I learned that somebody in between talked to my reflector. And if I send and repeat the query again a second after, I don't see that change. So I just see a 1. So consider a scenario now that there is a blocking happening between site and reflector. My first IP ID query is going to show you 7,000. The second one is going to be 7,001, and the third one is going to be 7,002. So I see a jump of 1, 1. So I learned that nobody could talk to this reflector or talk to this reflector at a time. Bear with me in the third case, when there is a reflector to the site being blocked, I will see 7,000, 7,002, but the responded reset won't get there, so there's going to be a retransmission happen here, and I'm going to see a 7,004. So I'm going to see what? 2, 2. So let me put this all together. In the first case, when there is a site to reflected block, the deltas are 1, 1. In the second case is 2, 1, and in the third case is 2, 2. And this is when nobody else is talking. But as you can see, there is 3 scenarios, and there is 3 different delta IP IDs. So it's detectable. And of course, you can say that, hey, Roya, this machine, this reflector that you're using is going to talk to so many other people, so the IP ID is going to be full of noise. Yes, you're right. And for that, we can do several things. For example, we can amplify the signal. Instead of sending 1 spoof scene packet, we can send 10. So instead of jump of 2, we can see a jump of 20. And for a variety of reasons, we repeat the measurement because a packet can get lost. The reflectors might have a sudden burst of traffic. And we, of course, use a statistical modeling to be able to come up with a technique that is statistically robust, which I'm not going to talk about. So this was a spooky scan, but the spooky scan wasn't ethical because we didn't separate who's the reflector. We just used the technique. And it wasn't also scalable. So we came up with a follow-up system, which is Augur. And this is the overall view of how Augur works. It scans the whole IPv4, finds reflectors that follow global IP ID behavior. Then it's check whether they're reliable, they're a stable machine, there are good machines to do measurement from them. Then we decide what type of sites we are interested to measure globally, what we're interested to know being TCP/IP blocked globally. After deciding that, then we schedule measurement and run our spooky scans for all the sites and reflectors we selected. And then we looked at the data and tried to detect and validate the blockings that we detect. We measured. I started talk by saying that there were 3 key challenges existed in previous work. One of them was coverage. How Augur is going to help us with the coverage? Well, there are 22 million global IP-ID reflectors available globally in more than 256 countries that we potentially can use. So it's really scaled up what we could possibly do. The second best case we have is 10,000. You might say that, well, there is some traffic, some CNAC and reset that you're generating between the reflector and site. And if there is a DPI between these two and it's sensitive, might still cause ethical issue. Well, I agree. And for that reason, we're not running measurement from end IPs. We're using routers. And we call them infrastructure routers because they're 2 hop back from the end IPs. Even with putting such a harsh constraint on the number of vantage points, we still have more than 50,000 routers, infrastructure routers, that we can measure TCP/IP blocking from them. The best second option we have is actually asking users around the world to give us a consent to run sensitive measurement, and this is a matter of tens. We're not depending on end users helping us, and we can just run a measurement continuously. So the data collected from Augur is obviously continuous. When the technique was established to test the technique and show that it works it's actually a scalable system for measuring TCP/IP blocking globally, we selected 2,000 reflectors in 180 countries. We chose sites in 2,000 sites, 1,000 of them sensitive website from a NGO called Citizen Lab. So we borrowed like 10,000 websites from them, and we added thousands websites from Alexa, top 10K randomly selected. So we had these sites that we wanted to see from these 2,000 reflectors globally, how they are being blocked, or are they being blocked by TCP/IP. We ran a measurement for 17 days, and we looked into the data. For example, we found these are the top domains that are being blocked from the site to the reflector. You can see the human rights website state on the top, and the others are hate speech or basically live journal, military website at the top. One thing interesting that we found out is at the 6th website, rank 6, we have amtrack.com, and it's being blocked in more than 100 countries. And the reason it turns out is because Amtrack is using possibly using a cheap DNS resolver, which does HTTP redirect, and the IP is also redirecting some sensitive website, and it's a collateral damage, and that's why Amtrack is being blocked. We found NSA.gov being at the top for reflector to the site blocking, although the technique is not going to help us to know where in the past the blocking has happened in this direction, but considering the nature of the website, we know that possibly NSA.gov doesn't want traffic from certain countries, so they actually do IP prefixes block for some countries. And this is a very common practice that the content delivery networks also doing. When there is no need for providing a service to a certain part of the world, they just block the whole prefix for that country. And this is a study that one of our students right now doing, which is understanding internet balkanization, where servers decide to block content for the globe, not only the governments of that country. So now we have the Augur. Augur is scalable, it's ethical, it's continuous, we can run these cool measurements. You might say that, well, to be honest, now many websites are hosted in the same IP, and because of the collateral damage of IP blacklisting, governments might not be prone to use that often. Actually, you might have heard about DNS poisoning or manipulations, and you are right. Actually, there are many countries that do censor traffic in following different techniques, and DNS poisoning is one of them. So the idea is when you type blah.com in your browser, the first thing happens is a DNS query. Hey, who has this blah.com? And the response is going to be the IP. And usually the governments poison that response by sending you a different IP. So how can we detect that globally, continuously? Is there a side channel? Yes, we have a technique that I cannot go to details, but we are upgrading and deploying a technique called satellite, which was originally developed by Will Scott at University of Washington, and now he's a postdoc at our group. And we added the lessons that we learned in another work that I did from DNS poisoning to the satellite, and we're capable of using almost 4 million open resolvers that exist to be able to run measurement from them. And if you want to be ethical and if you want to only run measurement from infrastructure machine, then we have 7,000 of them distributed globally. And we can detect that as well. Well, you might have heard about keywords blocking or application layer blocking. Like, for example, Chinese government does that. Let me just explain that. For example, if a traffic that is passing a deep packet inspector in China has a keyword that the government doesn't like it, then what they do is they basically drop the packets and send a reset to the both directions. So the server and the user both think that the connection is being terminated. Is there a way that we can have another side channels to be able to detect that? Well, this is the work that we are currently working on with Michigan folks and students that in our department. And we looked at different type of protocols existed, and it seems there is a protocol called ECHO, and the ECHO protocol, which is predecessors of a ping, is whatever you send to a machine that is running ECHO, it's going to send back exactly the same thing. So you send let's say, get http.google.com, it's going to send you back that. How can we use that to measure keyword or URL blocking? Well, imagine you send from your measurement machine, you find the ECHO server in China, you send the get http.google.com to the Chinese ECHO server, it's going to send that back. But the DPI is going to think that this is coming from the users and that has the keyword that shouldn't be there. So it's going to send a reset. To the measurement machine, instead of receiving the request that I sent, I'm receiving a reset. So I can detect that somebody in the traffic was not happy with these keywords. The ECHO protocol is just a sample of the protocol we are using. There are much more to add to this QUAC, a system that we're building to continuously and globally tracking keywords and URL blocking. So there are still lots to do. There are still more side channels to discover. We're interested to know about IPv6 side channels that we can use. We want to know about mobile networks and so on. But this is just a basic introduction of a project we call Censored Planet, a system that is aiming to provide an unprecedented level of data on different layers for internet censorship. We plan to run this. We're close to run everything in daily or weekly, better to say. And we're working on ways to be able to visualize the data, to communicate this data to political scientists and social scientists, and find ways to compare this data. Let me emphasize again that having these data will help us to be able to bring transparency and accountability to instances where governments practice internet censorship. It helps us to know how to come up with a better defense technology, where to deploy that. It will help users around the world to know what they're missing out. And more important, help diplomats and policymakers to know what's happening in reality and know better ways to deal with it. Or in another way, guarantee a democracy for all. That's it.